Okay, so now that we finished modular arithmetic, we're going to be going on to RSA, or reverse Shamir-Adleman, which is three surnames. So RSA is an asymmetric crypto system named after its founders. So it was founded by reverse Shamir and Adleman. Wow. Okay. So it's favored for its simplicity, which is also one of the reasons why it's one of the first, if not the first, crypto systems that one learns about. And it has been in use since like 1980 something, or probably earlier than that, which is why it is favored for its the fact that it's been tried and tested, which is why it's so widely used. And it's like, so remember that for every asymmetric crypto system, we need to have a hard problem as well as a trapdoor function. So for RSA, our hard problem is factoring integers, and our trapdoor function, wait, no, never mind. For factoring integers, let's say we have two large primes, p and q. It's very easy to get n equals p times q because you just need to multiply. But it is really hard to get p and q from n because it is really slow and it takes a lot of computation because you need to try a lot of values of p and q. Next slide. As for the trapdoor function, it is exponentiation modulo n. So let's say we have n to the power of 3 or some small known e, could be 5, anything. It is hard to recover n without knowing the factorization of n. And so this trapdoor function is dependent on the security of our hard problem, which again is the factorization. Everyone following so far? Okay, nice. Moving on. RSA is used in many things in the real world, and one of which would be the JSON web token. So for those of y'all who went for the web workshop, I'm not sure if they taught JWTs, but this is used in web a lot. And RSA is one of the algorithms that can be used to sign a JWT. Next slide. Now we'll be moving on to how RSA is done or it's implemented. So we'll be starting with our public key generation. So let's pick two large primes, which are anywhere from 512 to 204 bits. Actually, it can be larger. It will just take a long time to generate. And it cannot be smaller because otherwise it will be insecure. So let's say P is around 2 to the power of 512. And Q is also around 2 to the power of 512. And after that, we'll calculate n is equals to p times q. So, wait, can you back? So, let's say n equals to p times q. What is the bit length of n? So, remember p is around 2 to the power of 512 because it's 512 bits. So, what is the bit length of n? Anyone would like to try? What is n approximate to? 2 to the power of what? Yeah, correct. So the n is 1024 bits, and that means that n is around 2 to the power of 1024. Next slide. So once we have n, we will pick a small exponent e, and in RSA it is usually 65,537, but 3 and 17 are also used quite a bit, although they do have some drawbacks, which we'll get into later. Next slide. So once we have done that, we have our public key, which is n as well as e. So these two integers are all you need to encrypt, which is what we'll be going through now.
So I'll be doing a demonstration of RSA key generation in Python. So the general idea is very simple. So like from a Python shell, we're just going to do from crypto.util.number import this very handy function called getPrime. So what getPrime does is that getPrime will essentially takes a integer as input and it returns a prime that's that number of bits long. So for example, if I call like getPrime, let's say like 2 for example, it returns 3 because 3 is 2 bits. 3 is like 1 1, which is 2 bits. So that's what getPrime 2 returns. If I do getPrime 1, it's nothing because there's no prime that's 1 bit. And if I do this, I think at some point I could. Okay, maybe it doesn't even give 2, but it is what it is. So if I do like getPrime 512, I get this very big number which is a prime. How do I know it is a prime? It's very simple. I do this very handy function called isPrime that I also import from crypto.util.number. And if I do isPrime getPrime 512 for example, it says true because because get prime returns a prime number and its prime just checks that it's a prime number. How it checks it's a prime number, I don't really know, and I think we don't really need to know. That's it for key generation. So we will just do P equals to get prime 512, and then Q equals to get prime 512, then N equals to P times Q. So get prime 512 will get a random prime. So what you get for your P and your Q will most likely be different from the values I'm getting. So for example, like my N is going to be this. When you guys calculate your N and you ask it to print N, it's going to be a lot more different than compared to the N that I got, but it doesn't matter. And then we define our exponent, E, which usually is 65537. In some challenges, you may see this term being used, 0x10001. This is it's the same as 65537. It's just the same number. This is in hexadecimal. This is in decimal. And once you do that, your public key is going to be N and E. That is more or less the first half of the key gen that is done. We will deal with the rest later on. Any questions so far? All right.
Okay, so now we will be going on to encryption. So first, let's convert a message that we want to encrypt. So let's say we want to encrypt M is equals to I.YCEP. Oh. And we convert it to an integer, so we can use bytes too long. So let's do M int is equals to bytes too long. I'll just write BTL for bytes too long because it's really long. Yeah. So we can convert it to an integer by other methods, but for now we can, or should I say, the most convenient one is bytes too long. So next, we can calculate our ciphertext, which is C is congruent to M to the power of E modulo N. Or in this case, because our integer variable is called M int, we can do M int to the power of E. Everyone following so far? Okay, great. So once we have C, we use the smallest positive value of C. So toy example here. Let's say C is congruent to 10 modulo 7. But this will never be the case for I.YCEP because 7 is a prime. We will pick C is equals to 3. Following so far? So let's say C is congruent to 21 modulo 10. What will we pick for C? 1? Yeah, correct. We'll pick C is equals to 1. Okay, so that is it for encryption, and we have our ciphertext. Now David will be going through.
So as is with asymmetric crypto systems, you only need the public key to encrypt messages, which is why we're doing encryption here first as a demo before we find our private key, which Jerome will go through later. So for now, I am going to very quickly import another function, bytes to long, as well as long to bytes. So those are our conversions. So we have our N and E from before. How we're going to encrypt is, let's say our message is I.YCEP. We are going to do M equals to bytes to long of this value. And then the encryption is very simple. So C is M to the power of E modulo N. So in RSA challenges, typically you're just given C as a number, but sometimes they may give like they may give C in bytes, in which case you'll be long to bytes of C, which will be this value here. As you can see, C is very completely like large and very different from our message M. Because like M to the power of E is being used, so it kind of like jumbles it quite a lot. Yeah. Jerome will bring us to the next part, I believe.
Yeah. So now we will be going back to our slides. Yeah. So now that we have encrypted our message, the next logical question is what about decryption? So if we recall, we have C is congruent to M to the power of E modulo N. So if we didn't have the modulo N, we could just take the if root. But because we are working modulo N, we cannot just do that. It will give you gibberish. Next slide. So this ties us in back to Euler's theorem. So we remember that Euler's theorem states that for any A and N, So let's say n is equals to 35 and a is equals to 3. Because a is co-prime to n, a to the power of phi n is congruent to 1 modulo n. Make sense? Make sense? So again, we calculate our Euler's torsion function. I will not be going through this because we already went through it. But for RSA specifically, n is equals to p times q, which is very specific because this means that it is easy to calculate our Euler's torsion function. So since it's just 2 primes, we can calculate p minus 1 and q minus 1, and we can just product the two of them. And after that, we get our Euler's torsion. Okay. So again, since n equals to p times q, our phi of n is just p minus 1 times q minus 1. So you'll see here on the whiteboard, I specifically picked 35 because 35 is equals to 7 times 5. So phi of n is just 7 minus 1 times 5 minus 1, which is 6 times 4, which is 24. Next slide. So we want to find a value of d such that when we raise m to the power of e to the power of d, we get back m. So if we simplify this, I'm going to move to this whiteboard here. We get n to the power of ed is congruent to m modulo n. And if we manipulate the equation more, this right hand side is congruent to m times 1 to the power of k, which is congruent to m to the power of 1 times times n to the power of phi of n to the power of k. Oops. I'm not going to write the modulo n here because it's not enough space. But after that, we can manipulate the equation one last time to get n to the power of 1 plus k times phi of n. Everyone following so far? Y'all understand how we jump from this line to this line and to this line? Yep. Alright, great. So next slide. Now once we have done that, I'm moving back to this whiteboard. We can compare the left hand side and right hand side, and we can deduce that e to the power of d is equals to 1 plus k times phi of n. And this is over integers, not modulo n, because they are just comparing exponents. And since ed is equals to 1 plus k times phi over n for some integer k, this is very reminiscent to our earlier equation where we can convert it into ed is congruent to 1 modulo phi of n. Everyone following so far? Okay, great. Since e times d is congruent to 1, if we want to quote-unquote divide both sides by d, or in modular arithmetic, we want to multiply both sides by the modular inverse, we can see that, not d, e. We can multiply both sides by the modular inverse of e to get d is congruent to e to the power of -1 modulo phi of n. And we remember earlier when we were generating the public key that e is prime. So this means that if phi of n has a factor of e, which is unlikely, we can get the modular inverse of e because it exists. However, if phi of n is divisible by e, which means that there is no modular inverse, we just regenerate our parameters because it is so uncommon. So, offhand question here. This is not in our scope today, but what is the probability of there not being a modular inverse that exists? Expressed in terms of e.
We can assume for simplicity that phi of n will be a random number, and recall that when we were doing inverses, we know that a number doesn't have an inverse modulo if their GCD is more than 1. Like for example, the reason why 3 has no inverse mod 6 is because 3 and 6 have a highest common factor that isn't 1. So in this case, Jerome is asking for phi n, let's say a random number, what is the probability that E inverse does not exist?
This is the okay. So the probability of this happening is the probability of phi of n being divisible by E, which, if we recall, every E numbers have a factor of E. You all understand that so far? Which this means that the probability of phi n being one of those numbers is 1 over E. So that is our probability. And in RSA, E is usually 65,537. And 1 over 65,537 is really small, which means that we will, in practicality, rarely hit it. I would not say never, because RSA encryptions are done more than 65,537 times, but it's rare. So now we'll be moving on to our private key generation. So next slide. We calculate phi of n, which is equals to p minus 1 times q minus 1. And we use this to calculate our d, which is congruent to e to the power of -1 modulo phi of n. Everyone following so far? Alright. So after that, we have our private key, which is d. Make sense? Okay. So now we'll be going on to private key generation in Python. So David will be demoing.
So as we've mentioned before, to calculate the private key, we need to find a d where ed is congruent to 1 mod phi of n, and usually we kind of just call it phi in this scenario because the context is quite clear that it's phi of n, and in order to do that, we need to find phi. So the security of RSA is that we need to find phi, which we know is p minus 1 times q minus 1, but the public key only gives us n and e. And because n and e, n is p times q, to find p and q, or at least one p or one q, we need to factorize n, which is hard. This is why RSA is secure, because unless you know the primes, you can't really derive the private key. So to derive our private key, from p and q, which we have during key generation, we do phi equals to p minus 1 times q minus 1, and then we do d equals to power e inverse of phi. The chances that this works is very, very likely. So it's near guaranteed that this will run fine. If not, you have to regenerate your p and q. With that said, oh yeah, and then that's basically the private key. So now d is our private key. Yeah. Any questions?
Alright. If no questions, we'll be moving on to decryption, which is just as simple as encryption. So let's say we have our ciphertext C. All we need to do is just calculate m is congruent to c to the power of d modulo n. We're done. We just need to convert this back into bytes. So let's say we want our byte equivalent to be, or rather we converted it to integers using bytes to long, which is in big endian. We can just do m bytes is equals to long to bytes m. That's it. We're done. So now David will be demoing.
Yep. So as a demonstration for decryption, so recall we have our message and our ciphertext from before. To decrypt, we're just gonna do m underscore, so I don't overwrite my variable m, to be pow c d n. So as we discussed earlier, we found the correct private key whereby c to the power of d mod n by the logic that Jerome has written out on the whiteboard will give us our message m prime. And if you look at the values m prime and we look at the value of m, you'll see that they are completely identical. That's how you know that the decryption has worked. And generally, if you want to convert it to bytes, which would happen very frequently today, when you do long to bytes, you'll see that it returns the original message here. So this is how you encrypt and decrypt using RSA. Yeah.
So have you started? Okay, so now we're moving back to the slides for an exercise. So we remember that RSA uses these 5 variables, n, c, e, d, and n. So next slide. Which one is the public key? Anyone want to shout out? Remember, the public key is the one used for encryption. C is the ciphertext.
Oh.
Unfortunately, that's not correct.
M, E,
M, E, and N. M is the message you're encrypting, so no. But the other two are the public key. Next slide. So now that we have the public key, which one is the private key?
N, D.
D. Yeah, that's correct. Next slide. Which one is the plain text?
M.
M. Yeah, correct. Okay. So next slide. After we have completed encryption and decryption, we'll be moving to signatures. Next slide. So other than encryption and decryption, we can use RSA for signatures, which is a characteristic of most asymmetric crypto systems. So in RSA, instead of using the private key for decrypting, we can use it for signing. So only the sender has their own private key, which means that only the sender can sign messages. But because everyone has the sender's public key, everyone else can verify the signature. Next slide. So the steps for signing goes as such. Let's say we want to sign our message I.YCEP again. So M equals to bytes I.YCEP. And we hash it with some hash function. So let's say SHA256. So we can do H is equals to SHA256 M. So a hash is a one-way function that is mathematically impossible to reverse. And the reason that we want a hash is because we don't want any attacker to sign some weird message that produces some characteristics. Like for example, we don't want the attacker to be able to sign a very small message. So once we have hashed it, we convert it to an integer H. So we can just use bytes to long again. So small h is equals to bytes long of big H. Now we calculate our signature, which is S is congruent to H to the power of D modulo N. And after that, we pick the smallest positive value again, and we are done. So again, David will be demoing.
So as a demonstration, let's say our message is our I.YCEP and we want to sign it. So what we'll do is that we will just use SHA256 as our hash function. You can use like any other hash function as long as it's secure. So our hash is going to be SHA256 of. Since M is a number, we can just do like string of M dot encode. This will basically just encode M as a string and then encode it to bytes. SHA256 takes a byte output, and when you call digest, it will return a string of 16 bytes. So because it returns a string of 16 bytes, this is the hash output of string of M dot encode. And for those wondering, like string M encode is essentially just like, so recall that M is just 315 ... String M encode is just the byte string of M. So once we have our H, which keep in mind is exactly 16 bytes long, we will then convert it to an integer. So small h is going to be bytes too long of big H. And then to sign, we just do signature is pow H D N. So we use the sender's private key to encrypt our hash into this. Yeah. So this will be our signature, for example. It will be different for each of you all, but that's the general idea.
Yep.
Any questions?
Alright, so now we'll be moving on to verifying our signature. So just like how we have encryption and decryption, we have signing and verifying. So again, we hash a message. So I'm not going to write this on the board. I'm just going to say H is equals to ... So we just hash it again. And next slide. We convert the hash to an integer H, which is again small h is equals to LTB or long to bytes big H. And after that, since we have our signature, we can check if S to the power of E is congruent to H modulo N. And if it is, then it's verified. If it's not, then oh no, not verified. Someone tampered with it. So we'll be doing a demo of verifying.
Alright, so if you were to go back to here, so we have our signature S, and then we have our. So typically, what happens is that when Bob sends a message to Alice, when Alice sends a message to Bob, Alice will send the ciphertext and the signature over, So what we're going to do is that for Bob, if Bob is going to decrypt the ciphertext, so Bob will just do m equals to power c d n, where Bob uses his own private key to decrypt this. Then to verify the signature with this signature over here, Bob will, since Bob is able to recover the message, he will then hash the message. So Bob is going to do this, and then Bob is going to do this as well. So now he has H and he has S. And because S is the hash encrypted with Alice's private key, Bob will decrypt it using Alice's public key. So because ED is 1 modulo phi of n, if E is a public key, D will decrypt it, and if D is used to encrypt, E can be used to decrypt. So he will do pow S E n, and this will get him another value which we'll call his HH. So our 1H is the hash of the decrypted message. Our double H is the decryption of the signature, which should be the encrypted, it should be the hash. So to verify, we just check that the hash that we got is the same as the hash that the signature is supposed to represent. So the reason why we use signatures like this is to essentially ensure that what we receive is accurate. So for example, if let's say Mallory were to modify the ciphertext to some number, when we decrypt it, we get a different message, and so our hash of that message will be different than the one that Alice gave in the signature. So this is how an asymmetric crypto system uses signatures to ensure integrity is upheld. Yeah.
Yeah. So now that we have gone through both signing and verifying, the next question is, why does verification work? So this is the same reasoning as encryption and decryption. So if we recall earlier, we have m to the power of e to the power of d is congruent to m modulo n. Here we have h to the power of d modulo e is congruent to h modulo n. Everyone following so far? So this is because, again, when we have h to the power of d to the power of e, we can expand it into h to the power of e d modulo n. And since it is again h to the power of 1 plus k times phi of n, phi of n, modulo n, but I don't have space to write this here, it's just congruent to h. So everyone following so far? Any questions? Alright, if no questions, we'll move on. So now we have reached the first two practice challenges of today. So these two challenges are on the CTFD. They are called 7A really secure algorithm and 7B really secure signature algorithm. We'll give you all about 10 minutes to do the first one.